So, good afternoon, good morning, good evening to everyone out there. Thank you so much for joining our Tech Day session with Telescent. Today we are joined by Bob, Alan, and Dave, who is the second Bob Shine on the screen. So just a few navigation tips. For any chats, you guys are more than welcome to say hi in the chat and make some conversation, not too much, because we need the attention here on the screen. Q&A, any questions that you have for our panelists, please pop them into the Q&A section. We will be keeping an eye on those and of course answering it as we go. And that's about it. Bob, over to you. Thank you so much for joining, guys.
Well, thank you for inviting us to talk. I'm definitely looking forward to presenting this material. A little background on myself. I'm Bob Shine. I'm head of marketing and product management at Telescent. My colleague Alan from Telescent is the head of business development and sales. And then Dave from Mox is the senior vice president of engineering and planning at Mox. And he'll give a little background of how service provider is using automation of interconnections and diagnostics in a network. I want to start with just an introduction of the product and why we might care about automation and remote diagnostics. And I'll do that with a couple of pictures and then a quick video of our system. And then invited Dave to present just to give a little view of why it's needed for a network and how this can improve operations and service, customer service within a network. With that background, I'll then go into details of how the system works, give you an overview and actually some videos of the internal system, the algorithm that helps us scale up to the 1,000 ports in the system, and a detailed reliability of the system, because clearly if you're operating a system remotely, you want to make sure it'll work. One of the challenges of putting automation networks has been the upfront cost and the challenge with scaling. And so I want to discuss our robust approach to do that, a way to have a low upfront cost, low initial CapEx, and a way to scale from just a few ports to the 1,000 ports or more in the system. And that'll also involve the software integration as well. I'll then talk about some use cases from service providers that Dave covered, as well as multi-tenant data centers, and then some large hyperscale buildings and how they use the system. I'll finish with a roadmap and then future improvements, give a summary. I want to start with just some pictures, and I didn't have to search far to find these. These are from Reddit threads, CableFill and CableGore, and I'm sure this is not what your data centers look like. But the challenge is this is what a lot of them do look like. And it's not just a local problem. This is actually a universal challenge of how do you manage fiber and networks as they get more complicated and scale. And of course, no one designs a system to look like that. You always start with an initial system that all the cable is managed well and easy to change. But as you make configurations and changes in the network or add more equipment, it kind of evolves into that picture, that lower picture there on the left. The benefit of an automated or robotic system is that once you cable up the system, you don't have to make any changes. The robot handles all those changes. And so I like to say, you preserve day one performance with fiber layer automation. And the way I like to say is how do you manage disconnects? Clearly, most data centers get revenue when they provide initial service to a customer. And so there's a large focus on managing that initial connection, good inventory tracking, good fiber layout. But when a customer ends their service, there's not as much focus on disconnections. And that's where I think a lot of this complexity arises from, is some shortcuts taken on the disconnect side. And that's where again, with the robotic system, it's typing in the order to make the connection and just typing in another order to disconnect the system, and it manages it very well. So this is a video, and I'll turn on the video so you can really see what the system is before we go into the operation.
The cross-connect is performed by a telescopic arm with a gripper to move a specified connection and fiber to the desired port. Before plugging in the fiber into the connector, the end face is swiped on a cleaning fabric within an automated cleaning cartridge. This step ensures that very low and consistent insertion loss is maintained during operation. The cross-connect is typically completed within a few minutes.
So you can see that's what we'll be talking about for the rest of this webinar. I thought that video would really help you understand how it works. Another key feature of the system is that we can add diagnostics as well. So there's some space on the top where it can plug in everything from an OTDR to light sources to help you understand the network performance. And this is integrated into our API. So it's a single command to request an OTR trace. Nice thing about that is you could do an OTR trace on initial installation of the cable, kind of get a birth certificate or a birth record of the system, and then monitor it over time to make sure there's been no degradation or issues. If there's a customer issue, you can make a disconnect and run that cable, an OTDR trace on that cable to understand where the problem might be. And so the diagnostic capability of the system is also very important as you think about managing a remote system. And with that background, I want to turn it over to give you a service provider viewpoint on why this might be useful in a system. So I want to turn it over to Dave Bigelow now, who, as I said before, is the Senior Vice President of Engineering and Planning at MOX.
Hey, welcome. Good to be here. Thank you all for joining. And I'll just give a little bit of a brief overview. I guess go to the next slide. Yeah. So who is MOX? So MOX is a nationwide long-haul provider in the United States with connections over to Asia. Some of the services that we offer, wave services, dark fiber channels. Wave services, those are your 100 gig services. And the dark fiber channels are a bring your own modem type of service where after you've already invested in your, you have the modems and it's a capital investment, you can use those on our network. And of course, we put dark fiber in the ground, we build cables, and we sell that dark fiber to customers. So throughout MOX's history, for the since inception, MOX has used cross-connect panels, remotely operated cross-connect panels, and to help provide the services and to do to provide services and to be able to remotely test connections, remotely test our services. And some of what we get out of the constant monitoring of is the continuous fiber testing, historical records of all test results, and cable fault isolation. So since, as I was, the slides are a little out of order for me here, MOX has used robotic cross connects since inception. We do the remote test and provisioning of fiber. We can do service restoration with it and continuous fiber testing through using our remote test sets. We're able to, with the system that we've set up in the robotic cross connects, we're able to constantly test the fiber, get a historical record of all the test results, and be able to remotely provision, test, respond to our customers in a timely manner.
So Dave, what you have here in the picture, like in the middle is a cable has a high strand count, like maybe 864 strand, and it's going between two city locations. And you're terminating that high strand count cable then on the Telescent equipment, and that's where the remote monitoring sits. Maybe you could describe that process a little bit to the audience, like from day zero and throughout the life.
Yeah, we've invested in the remote reconfigurable cross connects. Because as we put the cable in the ground, it's a very large capital investment for us. With this asset, we want to be able to protect those assets. So by using this, we're able to constantly monitor, constantly test the fibers in the network, and we get those test results. They're stored. We use the cross connects for testing on a consistent basis, for turning up new services, for being able to provision the services rapidly. We have another slide in here which describes a little bit better our deployment. So maybe we can. So between Seattle and Washington, Seattle, Washington, and Portland, Oregon, we've put a 864 count cable in. You know, we have deployed the robotic cross connects on there along with the remote testing capability. This allows us to have a constant inventory, be able to know the status of the fibers. We're able to test every fiber in the cable. We're able to respond to fiber cuts, be able to know immediately when and if there's an issue, and we're able to then dispatch crews for restoration. Like I think a lot of people on the call, you know, because we're across such a wide geographic area, being able to have technicians at every single location in the network isn't feasible. So the remote test capability allows us to span great geographical distance with and be able to provide those near real-time diagnosis for issues, be able to provision services. And so it really helps us to provision the services very, very quickly.
Right. So I think that's the key, like you said, is being able to understand the high value asset that you put in the ground. The construction is very expensive, and to preserve that asset from day one, then provide guarantees to the customer as you're turning services over to them in whatever form that you do. And so I think that's why I wanted to kind of give a service provider viewpoint before we dove into the system on how it actually works. And so now I want to kind of explain, if you think about our 1,000 fiber system, so we have 1,000 ports on the front and 1,000 ports on the back. That means there's 1,000 fibers inside the system that might be connected port 203 to port 842, port 900 to port 12. And so you get this random connection as it evolves over time. And so the key algorithm of our system is the way that the robot will weave the fiber around all the existing connections that are in the system. And that's shown here, a very simple schematic where the robot will go around the fibers. Now, the key is as long as it only crosses a fiber once, then it will never make a knot. But if it makes a loop, that's clearly what the system needs to avoid. And so the system is done in a way that it never makes a loop. Now here, while we show the robot going around a line, what you see on the next system is a picture of all that. And so you can imagine how complex it is to find a route around the system, around all the existing fibers. And so that's where this image that's on the right here shows, and that squiggly line is actually how the rows move left to right. So as you see on the next one, the robot will reach down, but the rows will shift left to right. And so as the robot moves it to the next column, it is always preserves either going under the fiber or over the fiber. And as long as it does that, it will never make that loop that I mentioned before. Just a little background before we go into that, this is what the inside system looks like. So it's a magnetic latch inside the system. Outside the system, it's all LC connectors. So standard connectors for you to connect to the system. But inside there's a magnetic latch that the robot will grab the fiber and move it out. There's two states we call the allocated and unallocated. So clearly the allocated state is when the fiber connector is fully engaged. The robot can move it out a couple of millimeters, and then that is the unallocated. And then of course, when it's moving, it's in the open state. And I wanted to talk about the inside of the system before I show you the robot moving. This is actually one of the tests we do. We'll talk about reliability a little bit more later. As I say, clearly putting it in a remote location, you want to have full confidence in the system. And so this shows some testing that we do on the system where we'll just run the fibers back and forth. The way it works is there's a spool that the fiber is on the fiber tray. And you can see in this case, the spool moving back and forth as the testing system is moving all 96 fibers in a system. And so that's how we do the retraction and manage that. We test that retraction 100 times per tray, 5 times when the tray is put in a system. And we've done endurance testing of this on this rig here 15,000 times. So you can know with confidence that you can make connections over and over and over in the system. And
So
then as
Bob,
well-
on that picture, what you can really see as an audience member maybe is that what we are physically connecting with a continuous piece of fiber from a port on the back to a port on the front. In this case, they're all kind of in a standard matrix 1 to 1, 2 to 2, 3 to 3. And what we'll show next, I think, is how the robot manipulates that front side to move these fibers around each other to any port.
This actually shows the front image on the left, and the robot going down like we saw in that video earlier. And the image on the right is actually a picture from the inside of the system. And so you can see all the fibers going to the spine below the camera. So you can't see that right now. You just saw the row shuffle. And that's what I referred to before as the robot comes up. When it's on the top, the rows will shuffle either left or right, depending on if it went over or under before. The robot will drop the fiber off at the bottom, shift the bottom row over as well as the others, and then the robot will reach down and grab it. So it's going up the next column. You'll see the fiber in the gripper as it moves then to the next column. The rows will shift and the robot will go down and put it in that as well. So you can see the rows shift differently, again, depending on the prior state of the system. And that's how it kind of weaves its way around all this. You can see in this picture that none of the fibers ever cross or can rub against each other. They all have their own space. There you see it moving over again. And so seeing the inside of the system, I think gives you confidence that the algorithm will work, that the fibers will maintain their separation, and that we can find this path to any desired new port in the system. And again, that's based on the algorithm. The system I have behind me is an engineering system. We've actually run that system for over 300,000 connections. Our customers have tested it to 10,000 or more. But clearly the algorithm will work, and you can, no matter what the prior state of the system is, no matter what connections have been made, it will always find a new path. What the robot is doing right now at the end of the video is doing the cleaning. That box on top was the cleaning cartridge. And so before it makes the final connection into the new port, we'll do a swipe, and that helps maintain low loss and consistent performance. The typical loss is as you'd expect from 2 connectors. So it's 0.3 dB, and then it's going down to start a new connection. So that was kind of an example of a full move. As you saw, because it's mechanical, it will take 40 seconds if it's only within a column to a couple of minutes if it needs to weave over multiple columns. This is what a fully cabled up system looks like. Like I said, it's standard FC connectors on the back and on the front. This shows 1,000 ports in the system. You can't see it that well here, but there are modules in the system. So this here is one module up top, and it's 96 fibers inside the module. And the system is actually expandable over time. So you could start with a low number of modules in the system, a small number of fibers, and then expand that over time without interrupting service. So for example, you could start with 144 ports in the system, connect your customers up to those, and then as your requirements grew, you could add modules. You can always make a connection between any of the old modules and the new modules, so there's no separation between those. That's one of the first ways we can reduce that cost, as I mentioned before, as a way to grow the performance in service as needed. And then, like I said at earlier slides, once you make those external connections to the system, you never need to change those external connections or reconfigure, because all the reconfiguration is done inside the system. And in fact, Mox, when we installed the systems with them, we actually spliced into the back of the system. Since it's the front of the system where the connections are made, they wanted to minimize one of the connectors. And so we have that splicing option into the system as well. Talked about reliability before, and I want to go a little deeper into the reliability of the system, because clearly if you're operating something remotely, you want to be confident in the system. And so first, as I said, all the optical connections are mechanically latching, and so they don't require power. I talked before about kind of some universal challenges. I know some of the challenges for power in Africa are rolling brownouts and inconsistent supply of power. And so here, once the connection is made, you don't have to worry about power outages or anything like that. It doesn't interrupt service. As redundant power supplies in the system, we do have a Linux server in the system, and that's how we manage the system and track the changes. That does have redundant RAID storage. So if anything happens, you have a backup of all the connections that have been made in the current state of the system. We saw in the previous video the cleaning cartridge. And so one of the challenges with manual systems is the operators and the technicians may not always be consistent in how they clean. We've all heard the stories about just the lick and then wipe on the shirt. Clearly that doesn't provide consistent low loss. The robot that you saw is maintenance free. There's no oil in the system. There's no maintenance needs to be done to the system. And we've never had to replace a robot in any of our operating systems that are in the field. These systems are made at Flextronics. That's a contract manufacturer that's in the US. And they're one of the top 3 contract manufacturers in the world in terms of revenue. So they have production facilities around the world. The facility that we use is their Austin, Texas one, where they also make some Cisco gear and some Apple gear, some of the Apple MacBook Pros. So they're very good at making systems in volume. For our customers, we had to pass the industry standard tests. Some of our initial customers were telecom operators. And so we passed the NEBS level 3 test, and I'll show you later a video of the earthquake test for that. And then we passed field trials as well for a number of our customers around the world. One of the large Japanese telco operators was one of them, and they did 166 tests, including in the middle of a reconfiguration, pulling out the plug and seeing if the system can recover in the middle of that. That was one of the more challenging failures, because as I said, you can't, the algorithm won't work if it just goes to home at the beginning. So it had to start up in the middle of the algorithm, know where it was, so it could finish the configuration it was making. But they were very creative in all the tests they wanted to do. And then there are other customer trials that we've done, multi-tenant data centers and US-based ones as well. The system has been deployed in operation production networks. One of our earliest customers was some of the secrets agencies. And so we don't even know where they're located around the world. And they've been trained and done all the maintenance themselves for those 3 years that it's been deployed. So you have confidence in the system. I mentioned before the NEBS testing. And so this is actually the earthquake tests on the system. So let me get these videos started. And so we had to simulate an 8.3 on the Richter scale earthquake test. And first, to be able to get a shake table and actually move the system at that level is actually pretty impressive. But we actually had the system operating and making reconfigurations, reconnections as it was going through this test. And so the robot just reached down, grabbed a fiber and moved a fiber while it was on these shake tables. And so the system passed while doing that. So that's just one example of the tests that we've done. Clearly, there's all the other NEBS level testing in terms of flammability, resistance to electrical emissions and all that. But I thought that video was interesting to share. In terms of mean time between failure of the modules, the first thing, like I said before, is the fibers are latched. So if anything fails in the system, it doesn't interrupt traffic. We can see some of these elements here in the system could be failed and replaced relatively quickly. There are 2 consumable elements. One is the cleaning cartridge. So that swipe that we saw, that actually moves the cleaning cloth over after each swipe. And that needs to be replaced after 8,000 cleanings. And then the gripper, the thing that grabs the fiber and moves it, needs to be replaced after 16,000. Those are very simple 15-minute replacements. It's 2 screws and an electrical connection that need to be replaced. The robot, as I mentioned, is a 30-minute repair if you need to. It's a couple of screws and you take that out and put it in. It's a kinematic mounting. You can see the replacement time for these other components as well. So it's very simple to repair if needed. Like I said, we've had one customer that had to have done this all themselves after a roughly 4-day training on the system, and they've maintained their system for the 3 years that they've had it. So with that as background, I want to go into the question of how would you implement this? And like I said before, one of the challenges of automation has been the upfront cost and the scalability. So there have been systems like MEMS-based or piezo-based systems. And the challenge there is you have to put in the full system up front to have the capability to do the automation and the diagnostics. And that can be a very expensive approach. Our approach is a much different. And one of the challenges, as you think about automation, is you don't necessarily have the need to automate the full system. And so to use the MOX example with an 864 count cable, they put that in because it's very expensive to do the construction. So if you're running a route between, in Dave's case, Portland and Seattle, the construction costs are very high. So you typically put in a very large fiber count system that you plan to use over maybe a decade or more for uptake for customer service. But customers will only take a portion of that initially, and you'll plan to sell it out over time or sell the capacity over time, like I said, maybe a decade. But the challenge is you can't just say, well, I'm only going to automate 50 of those 800 fibers. You don't know which fiber you're going to need to have access to. And so that's, like I said before, the prior approaches to automation have had to put in the full system, full automation of every port up front. And so what we want to do is minimize that upfront cost, automating the system for the unused ports to allow automated connection to anyone and scalability so that you can start with a small number of automated ports and add to those as demand and revenues grow. And so that's what our robust approach is. So robust stands for robotic, unequal, single tier. And so it kind of mimics a manual patch cord system. So on the left would be a patch panel with patch cords between the system. And you would have the ports for all the fiber connections you'd have. Again, using an 864 count fiber, you would have termination of 864 ports on that patch panel. So we can do the same with our system, and you can land all the fibers on the front ports. But what we can do is only put in a few modules for the automated, what we call the automated patch cords. And so what we've done was we've actually separated, if you think about what our fiber module is, in the past, I told you there were fiber modules that were 96 ports, which would be 48 fibers if you count two ends. But what we can do is we can separate that front of the module, which is where the fiber ports are on front, with the gray portion here, which is where the fiber retraction is. So think about a patch cord and a port. And so what you can do is you can put in an unequal number of ports and fiber patch cords. And that allows you to have a low-cost way to land the fibers, because this part here, the ports is a low-cost piece, and a lot of the cost of the system is in this robotic patch cord, again, where those retractors and all the reels are, where the fiber is. So you can have a low-cost way to land all your fibers, and then have maybe 1, 2, maybe 3 of the robotic patch cords as needed. And the nice thing about that is the robot can use those robotic patch cords to go to any of the ports on the front. And so you have a low patch cord, a robotic patch cord, but you have access to every single port that's been connected to the system. So you don't know which customer is going to request which port. So it does meet that need of being able to address any port on the system. You can also still do the OTDR tracing. So we heard from Dave earlier that diagnostic was important. And so they want to be able to monitor all of their 864 fibers in the system to maintain reliability over time to preserve that asset and know that when the customer does request it, it'll be ready. And so they can periodically test all of their fibers in the system using the OTDR. The robot can go down and grab it and test it every quarter, every month. So I think that's a nice thing. And so I want to ask Dave, Dave was one of the first customers to use this robust approach, how it improved his implementation.
Yeah, so it definitely helps us, quite a bit. The any-to-any was a very, very important aspect of this approach. Many cross connects are a east to west configuration, and that presents a lot of challenges with being able to test in both directions by the nature of the configuration. So in this configuration, we really like the ability to be able to get to any of the ports, be able to do the consistent and persistent fiber monitoring on specified ports, but then also be able to do ad hoc testing at will. It's really important that we have the ability, if and when we receive troubles from our customers, that we can look in both directions. So the diagram here kind of depicts, just the OSP cable, that the long haul cable. But in reality, those fibers are a mix of facing the meet me room, as well as facing the outside plant, as well as facing equipment. So now we can connect equipment to the outside plant. We can connect equipment to the meet me room. We can look in both directions towards the meet me room and towards the outside plant and do either OTDR, visible light source, 1310, 1550, 1625 sources. So be able to measure power, be able to measure distance, and be able to ensure that when it leaves a particular port at site A, it shows up on the right port at site B, and we're able to then validate that the ports align where the records say they are. The other really important aspect of the automation for MOX is the real-time inventory, because you can label each of these fibers. You're able to know who they're assigned to. You're able to know the distance. You're able to know all the different aspects about them, and whether, really important, whether they're actually in use or not. Because if there's not a cross connect there, of course, it's not in use. So as long as you are have a decent way of tracking, what you're putting on the fibers, once that patch cord's removed, the fiber is open, and then it can be tested remotely. And you don't have to dispatch to a remote location to disconnect a patch cord that may no longer be needed. You can do that remotely and keep a clean inventory, keep a really good sense of what is on the cable and the quality of the asset. The other really important factor for us is being able to test those fibers at will, and rather than wait for an order to come in and then you need to go provision the fibers, and then you need to go, and then once that happens, you're looking and doing the OTDR test. If you see issues, you then have to figure out where those issues are, dispatch, and correct the problems. We're able to know that immediately before we ever we don't have to go out into the field, test the fibers, and then find out there's a problem. We're able to know in real time if there is an issue, where it is, and then take the appropriate corrective action.
Yeah, but I think there's an example of that. You had a tree branch with an aerial fiber, and you could monitor some loss over time and do a preventative maintenance before the failure occurred. So that's an example of being able to continuous test.
Of course, other examples are damage to the cable, malicious damage, people using cables for target practice,
Yes.
holes in cables, and being able to find those faults, going out and to go out and fix those faults, right away. Not all faults, even though some fibers may be broken in a cable, it doesn't mean that all the fibers are broken. And oftentimes a broken fiber may be on a port that's out of service, that's not in use, and you don't even know, because all the traffic bearing fibers are still passing traffic, they're in use, they don't show any degradation. So being able to remotely test fibers that are not in use is really one of the most attractive features here. The other thing that is really important is being able to have a record of all the historical data, and being able to then do and analyze over time any of the fibers in the cable, and being able to see if there's a particular degradation at a certain distance from the cable. Could be due to fire, could be due to heat, as Bob said, branches that have fallen on the cable, and so it gives us that remote capability without dispatching to a location to do all the OTDR testing. Another really important aspect of the automation is as you get large account cables, and if we just think of a cable like 144 count cable, and if you're doing a 1 minute OTDR trace, you're probably taking you 2 to 3 minutes per trace. So at 1 minute, that's 2.5 hours per 144 fibers. So to get through 144 fibers of OTDR testing is about what you can do in a single day. And as you get these really large count cables, that means there's a technician sitting at that patch panel moving from connector to connector testing each of those ports. And it can take days to get through all of the fiber and then collect the data. And then then you need to analyze it. Being able to set up the automation so that you can schedule all the open ports to be tested means that there's not someone sitting in front of the patch panel plugging the OTDR in to do the testing. Now it's about looking at the results and, with the appropriate software, being able to even automate that analysis and only highlight the fibers or the events that don't pass the thresholds set within the software.
Yep, no, those are great points, Dave. I definitely appreciate saying that. I think some of the other things is the things you don't think about is, like you said, the historical data. How did the technician, if it was manually done, name the file so you can actually go back and find the file? And then you mentioned also an OTDR. I'm sure this never happened to you, but I've heard stories of a technician having a dirty OTDR test fiber and basically moving that between every port and creating a problem with every port, spreading the dirt around the system. And so by having an automated system to do the reconfiguration as well as the testing, you can ensure the consistency of the performance and not add problems from the manual technician. So before I go on to the software side, the kind of summary of this is that this is a low-cost approach that duplicates the operations of a manual patch panel. So it's very simple for an operations team to come in and load the panel, but brings automation in a way that's a very low-cost approach, low incremental cost above the cost of the patch panel by adding the robotic system and the robotic patch cords, and then allows you to grow the robotic system as your revenue grows and the number of active ports grows in your system. Of course, the hardware is only part of the system of implementation. So I'll talk about the software integration as well. And Telescent has our virtual machine. So a number of our customers have started this as they've been waiting for the hardware to arrive, where they can use the virtual machine to start looking at operation within their system. And so they can download this, we can send it to customers. They can see the operation, they can start writing the scripts to bring that into their system and do system testing. It'll do the same operations as the hardware, so you can mimic all the commands that you need to send. Of course, it does it much faster. If you had a queue of connections to be made, it doesn't pause for that, but it can tell you the estimated time to do that. We do have a web GUI, and this is what it looks like. This is mimics the front of the system and the back of the system. So input and output, and you can actually, click on the module. So this is the module that's selected here. Click on that, and then do a connection to another one. So very simple kind of click and provision of the system. You need to unlock the port first to have access to make the change. But it's very simple operation. So you don't need to write a full script to integrate it into your operational system. If you just want to implement it quickly and do a click and provision type thing. For more detailed integration, we do have a REST API. So it follows all the open API specifications for commands and integration. It generates the code automatically for the platforms, and the tools are available. And so as an example, we had a customer do this, and they started with the simulator so they could start writing some of the software. They integrated into their operating system and business systems. In this case, it was Salesforce.com for their billing. It was iTrax for inventory, and then some other systems as well. And so again, it's very, very straightforward. If you think about our system, there's very little commands that you need to do. It's basically connect, disconnect, measure. And there's of course diagnostics if you want to, get a response back to confirm that the connection was done. But there's not a very complex system if you think about it. So it was relatively quick for this customer to integrate It was approximately 1 to 2 man months of development time for them to integrate our REST API into their operating system. So it's relatively straightforward to integrate. And so now with that as background, I want to go through a couple of use cases in addition to what we heard from Dave at Mox. And so just think about it, we're replacing a manual patch panel. Manual patch panels are everywhere. And so the uses run from lab use cases where you might be doing some development and testing different network configurations, multi-tenant data centers, transport like we heard from Mox, and then some cloud and hyperscale use cases. And so first, like I said, the first uses of our system was actually in labs. And this is a case where they wanted to test different metro configurations. And so they had different hardware that they wanted to test. They wanted to vary the hardware, vary transmitters and receivers, vary their fiber length. So they had different fiber spools in the system. And so the system let the Telescent system let them automate this testing process where it could put different elements in the system and make sure the service was maintained over that various network configurations. And this, like I said, was our first use case. We have this in many names that you recognize for the U.S. and international service providers and customers. In addition to Mox, we heard Dave talk about a long-haul network where they put it in their U.S. network. Caltrans is another customer. So it's California Department of Transportation. And in Los Angeles, they have fiber running along the highways. And these are actually the buildings shown where they implemented our system. So these are along the interconnection in the highways. And these are these large dots here are where these highways meet. They have maybe 72 to 144 count fiber running along the highway. This to operate their traffic management system. They have cameras at the highways, and so they bring that back to the system. The challenge what they have is they have fiber cuts. Everything from accidents along the highway to homeless people trying to break into these shelters or starting fires nearby that would then melt some of the fiber, for some of the cables. So they have those challenges that they wanted to manage. And so the diagnostic element was important to be able to see where a failure is, understand where they needed to send repairs out to, and then using the unused cable routed around so they could maintain service around the network. And so they had 7 systems that they bought. They were from 144 fibers per system up to, I think in their headquarters, they had a 560 count fiber system. And they've had this provision for a couple of years now through those locations. The multi-tenant data center is another very large use case. Clearly, they provide interconnections into their business. And so they have the meet me rooms. And some of those will have those pictures I showed before where it becomes chaotic over time if they don't manage their disconnects very well. And so this is where they can provide a virtual meet me room in a box. And so our system provides all the interconnection as required in the system. And so, what do we replace? We replace the manual process, which can take anywhere from 3 to 14 days, depending on how efficient the operation is. So receiving the work order, the paper process, the ordering the engineer and the technician out to facility. There might be some larger facilities that have multiple data halls on the campus. And so that might require the technician to go from not just 2 locations, but maybe through multiple intermediate data halls to make the connection. Once that's done, they need to record that and close out the work order and document the changes manually. And like I said, and as you heard from Dave, this manual documentation is where a lot of problems are. We've heard some stories from multi-tenant data centers where maybe 30% of their inventory is unknown because they haven't managed that disconnect process very well, and it's changed over time. There's another example of a merger that occurred in the US. And when the company took over, they actually spent 2 years rebuilding the inventory of all the interconnects because it was not tracked well. So they had to physically trace every connection to build their inventory, and it took them 2 years to do that. What does the system do? Well, in our system with automation, a operator sits down at the terminal, orders a connection. You can see here an example of what the point and click looks like. Port A to port B. and makes the connection. You can automate the SLA process, so you can have online confirmation of order. You can always track how all those requests are made. This can do an initial OTDR to confirm performance before it turns the connection over to the customer. So we think that's a very good use case, and it's been in process.
So Bob, I was thinking maybe go back to Dave on that one, because I think this is important. A lot of our customers are implementing portals for the first time for their customers to directly order services. And I think Mox has the same, and the manual process is pretty long. I don't know, Dave, if you could talk a little bit about the automation aspect of the service delivery.
Yeah, so we're still working through that automation piece with service delivery, but with respect to being able to provision right away, as the order comes in, we're able to then go validate the fiber, provision it through the system, and have test results in kind of record time. We don't have to dispatch to each location. So on the Seattle to Portland route, we're putting 5 units in. There's intermediate sites along the way, and even through those intermediate sites, we'll be able to test in both directions. So that part of the automation is really crucial to being able to deliver service very quickly.
Yep. And then a lot of people have heard about machine learning, with ChatGPT and others. And one of the challenges with machine learning and AI is the training that's run. And so for ChatGPT, it was 175 billion parameters that were run. For ChatGPT-4, it was 576,000 billion parameters. So actually approaching 1 trillion parameters with these data sets. And that takes multiple weeks. And I've even heard month-long training runs to develop the inferencing program to do that. The challenge is that there's different needs, and so if you think about those workers, the GPUs, the computers that use, they're exchanging data between every iteration. So it'll run, they'll get their intermediate communication, then they have to exchange the parameters in an all reduced type fashion. But there's different demands as you do this parallelism to break up this training run. And there's these charts here show different bandwidth requirements between different workers during the training run. And so we've worked with a professor at MIT to optimize the configuration, the network configuration, to optimize the training time. One other bit of background is because the data exchange has a bandwidth limit, the exchange of data can be almost half of the training time. So depending on the algorithm that's being run or the image recognition, it can be from 37 to 52% of the total training time. So this data exchange is actually a big problem in these large training runs. And so what this professor came up with was this thing called TopoOpt, but rather than having equal bandwidth between all the systems, it optimizes the connectivity. And so it might this might be a low bandwidth requirement, and this might be a high bandwidth requirement, and it moves the configuration so there's more bandwidth between these high demand nodes workers. That's possible because the requirement is stable and predictable during iterations. It's based on how the model has been parallelized through the workers. And they demonstrated through this TopoOpt program 2 to 4 times improvement in training. So what might have been a month is now 1 week. And that can have significant performance. I read somewhere that the training for ChatGPT-3 was about $87 million to do that training. So if you can cut the time in 4, I can see how significant that can do. Or it can let you run more trainings to get better optimization. So I think we'll be hearing a lot more about machine learning and training runs. And then another one that's also a hyperscale use case is data centers are built, you don't put in all the equipment up front. You try to put in a data hall, bring that up so you can start getting revenue from the data center, and then add capacity over time. And those networks are connected in the clone network configuration. So there's a leaf and a spine, so you can do any-to-any connectivity. But as you expand that capacity, you need to change the flow network. And so that one way that can be done is through electronic switches. But what's been done and demonstrated by Google is using using optical circuit switches to replace the spine layer. And they can then do this data center expansion much faster and save a lot of money in terms of OpEx and CapEx. And so that's another network use of our robotic automated cross-connect system. Talking about hyperscale, there's always a request for more connectivity. And so our system with 1,000 ports is actually the largest scale automated robotic system today. That's not enough for some customers. And so what we're working on is higher fiber count systems. And instead of using single fibers per port, we'll use 2 fibers per port initially. And so it becomes now a native duplex system where it's 2 fibers into the port. So instead of LC connectors, we'll use SN connectors. You can imagine going further and doing 8 fibers per port to 32 fibers per port as you see parallel optics and trunking systems coming in. So that means we just need to replace the fiber connector, the internal fiber connector with the magnetic latch, and change the gripper that grabs that fiber. The system stays the same, it's the same rack. The algorithm still works. It treats these 2 fibers as 1 fiber, so we don't have to worry about crossing those. And so there's a scale that we can go up. And so our current system today is what we call our generation 4, and that's 1,000 ports. Generation 5 is now using the SN connectors, and so it's 1,000 ports, but 2,000 fibers. So it's native duplex, and we've already built a module, and we then now need to build a system and test the capability with that. And then the further generation is then moving from the SN connector to an MT type connector, which can hold 8, 16, or 32 fibers in a system. One of the challenges of getting to those is actually just the diameter of the fiber. The ultimate scaling of the system is actually the fiber diameter that's in the back of the system and the density that we can get there. And so we're working with some fiber manufacturers to get the smaller diameter fiber that we can then combine into these 8 and 16 and 32 ports. As we're doing that, though, the orchestration and the network management is the software development that we're working on. So you can treat it as one large system as you put multiple systems together and just say, I want port 12 to port 8092 on the system. And so it's kind of our roadmap with the system. Just want to end with a little bit of the company overview, and then we'll take some questions if there are any. As I've mentioned throughout, the Telescent solution is operationally deployed here from Mox, who's had it in their network, but it's also been in other customers since 2018. We estimate that we've got over 1 million system hours to date and 1 billion port hours in operation. Mentioned that it's been NEBS tested and certified, passed numerous tier 1 trials throughout the world, Japanese and US customers. Production's outsourced to Flextronics, that's in their Austin, Texas facility. We shared all this information because we have a number of patents, so we have 56 patents issued and pending. We are a private company and we're venture backed, and so we've raised $40 million to date. We're based in Irvine, California, which is where I'm based. And for those that don't know California geography, it's just near Los Angeles in the US. And we think it's a unique product with a compelling price point that has a large market because it can be applied anywhere there's manual patch panels. And so with that, I want to thank you for your attendance. And here's my info, shine@telescent.com. Alan's is givenmeyer@telescent.com. And if you have any questions for Mox, you can reach them at info@moxnetworks.com. Thank you.
Thank you, Bob. Wow, that is quite cool. I'm just a bit concerned that I won't be able to post any pictures should this be implemented into data centers. But it's quite cool to see where this is going and how it can be used in the different use cases. Networks have different requirements, and yeah, it's quite interesting to see how automation is coming into something that has been done by hand for so long, right?
Right.
Question that I have, and I think before we end the session, if anyone has questions for the team here, the panelists, please pop them into the Q&A. I think my question would be is, the funniest or the weirdest incident that you guys have seen or know about regarding, you know, a fault, or because you mentioned, you know, there's people trying to break in or fires or anything like that. Any interesting stories you can share with us?
Sure, I'll share some and let the others think. So I mentioned the Caltrans network, and so that's Los Angeles. Like I started before, you know, all these challenges are universal, so this might resonate. So recently, the homeless people broke in, and they wanted to steal the fiber, or they wanted to steal copper, right? That's what they're breaking and trying to get. And so they took the system, but they left our system, and they didn't see the copper, so they left it alone. But what they had to do was they had to change the lock on the system, so there was a Wi-Fi type lock, so there's no external thing that they could break off. And then of course, starting fires, they would start a fire near the system, and it would melt the cable outside. Not a fun one, but a funny one. But the other thing I heard was someone wanted to just make it in a multi-tenant data center. They wanted to just do a connection. And so the technician went out, made a connection, and then the customers called up, and because of poor inventory, they disconnected the wrong customer and didn't address the customer request, and took them 8 hours to try and debug that disconnected main to find out who they actually disconnected. And so again, that's points to the need of good inventory and good accuracy. Because if you don't do that, what might seem like a simple thing becomes an 8-hour-long nightmare to try and fix. Dave and Alan, you have any other stories?
Nothing really funny. Most of them.
I think it's more painful than funny.
Yeah, exactly.
Yeah, I think of damage that we've seen, whether it's holes in the cable, trees on the cable that go undiagnosed until you need the fiber. So not really funny as much as painful. And then, it's a fire drill to get the crews out there to try to figure out, why fibers don't go as far as they should, where the degradation is coming from, and of course it always happens during holidays, at night, about 3 a.m. when these issues come up. So not funny, but painful. Being able to diagnose those issues before dispatching crews is a big time saver, and much more efficient. It can be planned much better. So all around, it's a better use of resources and a more timely resolution to any issues.
I think one other thing that I've heard about, and this is probably a U.S. problem more than a universal problem, and mentioned this before, target practice. So in the U.S. we have more guns than people, as you probably heard, and I guess in the Southeast in the U.S., Tennessee, Alabama, Mississippi, it's more common to have these issues with bullets affecting the fiber and using it as target practice.
Oh, wow.
But yeah, that's, I think, a U.S. problem more than anything else, where they just, try to shoot down. They don't know it's fiber inside. They're just trying to test their thing. But that apparently the Southeast is a very big problem, having damage by bullets.
One thing I have noticed when doing patching, right, is so we use high density patch panels where we can facilitate 144 cables. And what I found is that sometimes when doing patching, right, you think that you have connected the patch lead, but in essence, it didn't do the click. So does the system listen or feel for a click, or is that also a sensor that can tell you that a patch lead is not fully connected?
So we have, the way we would do it is there's an encoder on the fiber reel. So we monitor how far the fiber is pulled out, so we know it's going to the right port. And then, like I said, it's a magnetic latch, and so the magnetism actually pulls it into the system. So the robot isn't pushing it in; the magnet is pulling it in.
It's pulling it in. Oh, interesting. Yeah, that's quite cool.
Yeah. there's a question here I want to answer in terms of what skill sets are required for the system in terms of resource planning point of view on robotics. And so I'll use that example for maintaining the system. It's, like I said, very simple. The training that customers go through is 3 to 4 days here, so on how to fully operate the system. They'll do a cartridge replacement. They'll do a gripper replacement. We'll even have them change the robot. And that's all mechanical. So like I said, there's a couple of screws and then making a serial electronic connector. So it's a kind of technician level repair. In terms of diagnostics, there's some software. So it's scripting if you wanted to do a download of what the problem might be and diagnose that. And of course, we will help with the customers in that case. In terms of database solutions and security on the server, everything is fully encrypted on the server, and all the interface of the system is encrypted. So we have full security on that. So you won't have anyone be able to break in on that.
Yeah, that's an important point. I mean, security is, quite an important topic in the industry. So that's good to know.
Yep.
Any last questions from our attendees? Let's just give it another minute or two.
Yes, there's one more question about robotic failure. Were the arms damaged and tangle the fibers of the robot? So the first question is, people have this image of the robot going crazy. So what would happen if the robot just had an arbitrary movement? As you saw from the system, it's actually like an elevator shaft that the robot goes down. So it can't go across and damage the fibers that's in the matrix. It would be confined in there. There's actually a pressure sensor in the robot. So for example, if maybe a row was out of spec and out of space and it tried to push against it, we would notice that and it would stop operation. So we won't get this kind of crazy robot type activity to damage or pull the fibers. And then repair shim or do that's all kinematic mounting on that. Let's say the worst case happened, the robot failed, server collapsed, all the data was lost in the system. You can still rebuild the matrix, the connectivity matrix, because there's a sensor on every fiber. And so what we do is we would put in a new robot and have it go down and basically touch every fiber, and then it would identify itself. And that would then build up the connectivity matrix that was done. So even if there was redundant RAID storage, the robot failed, any backups were lost, you could still rebuild the matrix, rebuild the connectivity that existed in the system by having the robot basically touch every fiber and understand what was connected where. So we've gone through all those examples. So hopefully that answered that question.
I see there's an interesting question touching on heat load.
Oh, yeah. I didn't answer that. So it's a very low power load. So it's 50 watts when it's static, and then 500 watts when it's actually all the motors are moving. So it's very low power system. There's no fans in the system because it doesn't generate enough heat. It can operate over in extremes of 5 to 50 degrees Celsius. So it can operate in any data hall. You saw it's in the roadside systems, the roadside cabinets by Caltrans. So there's no very limited power consumption during operation.
So I see Jandra is asking around how long does it take to patch one fiber? That would be an interesting question to actually ask to the attendees. How long does it take you to patch one fiber for measurement? But Bob, please let us know.
Yeah,
I'm
so
sure it's
if
a few seconds.
So excuse me. So if it's in a column, it's 40 seconds. If it has to weave through every column, it's 4 minutes. So the maximum would be 4 minutes, but the average is about 100 seconds.
Look, it takes me a while to find the correct port.
Right.
So I'm not that fast.
Yep.
Cool. Well, I'm going to start thanking our attendees for attending today's session. It was very interesting. And to our panelists, thank you so much for joining, especially Bob, getting up so early to present to us. The recordings and slides will be shared with all of our attendees after this session. And again, a very big thank you to all the attendees and panelists. We will see you next time. If there's any last questions, please feel free to pop them into the Q&A.
Yep, and you have our email at the end, and we're certainly happy to receive any questions over email as well. And thanks again for everyone's time.
Thank you.
Take care.
Bye.